Okay,
Sorry, I just realized I was muted. Oh,
yeah,
sorry, go ahead.
okay. Welcome everyone to Bosonic Learning Theory Winter School Day. And yeah, today I'm very happy to introduce Vishnu Iyer here. He's final year PhD student at UT Austin, and he will be joining Maryland as a postdoc in this fall. So today he will giving a very interesting lecture on Fermionic unitary learning. And please welcome Vishnu.
Hey everyone, thanks Junsia for the intro, and it's nice to meet everyone. So yeah, I'm Vishnu. I'll be talking about some fermionic unitary learning um, results. And so I looked at the schedule from earlier, and it seems like you guys haven't really talked about unitary learning. So first, we're going to talk about what it means, like what the unitary learning problem is. Then we're going to give a recap on fermions, and then we're going to talk about learning a specific class of fermionic unitaries called the fermionic Gaussian unitaries. Um, and the point is going to be that like you can't learn arbitrary unitary operators. It's going to be very difficult, but we can look at some particular subset of unitaries to learn. And then um, fermionic Gaussian unitaries are a great example of this. And then we're going to look to extending this result uh, beyond just fermionic Gaussian unitaries. We're going to look at a generalization of this learning result. So I'm hoping to show you to introduce the unitary learning problem here, and then give you some techniques on how to learn structured classes of unitaries. And then maybe we can even talk about, ideas on how you can extend these things. Okay. So first, what is the unitary learning problem? So the unitary learning problem, for the purposes of this lecture, we'll consider a black box unitary learning problem. And what this means is we're going to have some access to some unitary operator. And recall that a unitary operator sends some quantum state psi to some quantum state phi. It's how we move from one state to another. In general, if this is if you have a pure state, if you have a mixed state, you act on it in the following way. And in general, unitary operators are what are like our standard quantum dynamics of a closed system. When you evolve a quantum state under the time-dependent Schrodinger equation, this induces some unitary evolution, and so you start from some state and you get a different state. Okay, so in the unitary learning problem, our goal is to learn some unitary that might be occurring in nature. And when we say black box, what this means is you have some unitary. You actually don't know what it looks like, but what you can do is you can take some input state rho, you can plug it into this unitary, and you get some output state rho prime, and this is what happens, right? Like U is going to act on rho, and you're going to give you some other state rho prime, and then you're going to do some algorithm. This is your unitary learning algorithm, actually. So this is going to be your learning algorithm, and the goal is to output some U tilde that's close to U. Okay, so the idea is you have some unknown unitary U. You can probe it, you can put input states, you can get output states, you can measure the output states, and you apply some kind of algorithm to choose what states to put in, to choose how you measure these things, and you use that to reconstruct this unitary U. Okay, and what do I mean? What do I mean when I say close by? So we're going to be using something called the diamond distance. Okay, what is a diamond distance? You should think of this as like a worst case distance. Okay, so I'm going to write down the definition of this diamond distance, and then I'll explain what it means intuitively. So max rho of, sorry, the diamond distance between, pretend this is a diamond. This is supposed to be a diamond. I'm just not very good at drawing. Um, so the maximum distance between U and V is, uh, or the diamond distance between U and V is the max across all states rho of this unitary tensor. There's a tensor product with the identity. The reason that this tensor product with the identity is there is just it's just there for like there are some like examples where you can take a state and entangle it with some other register, and two different unitaries would give you the same results if you just like looked at a local state. But if you look at the global state, then I guess don't read too much into this. Okay, so the point is you act with this unitary on this input state rho with U, and you act on this input state with V. And that what this is saying is it's just the worst case across all states of like distinguishing U on rho and then V on rho. Okay. What this is saying is if two unitaries are close in diamond distance, that means on every single state rho, the output states are going to be close. Okay. So if you consider any possible input, then the output states are going to be close in the standard state distance metric. So the actual formal definition doesn't matter too much. All that matters is this is going to be like a worst case distance. So the goal is in unitary learning, I'm going to make a bunch of these are called queries. Okay. These are called queries. I'm going to make black box queries to this unitary U, and I'm going to try to, the goal is to output. So the goal is to output some U tilde that is close to U in this diamond distance. Okay. So now I'm going to give you our recap of fermions. Oh, and by the way, if you have any questions, Jinsei, I don't know how this is supposed to work, but if you have questions, please raise your hand and like if you just speak and then I'll answer those questions. Um, so recap of fermions.
Yeah, I have a question.
Yes.
So by query, do you allow any arbitrary measurements? Like if you do you even allow like highly entangled measurements?
Yes, you are allowed highly entangled measurements.
So
The goal
basically
is just to,
any measurement is
yeah,
allowed. Okay.
correct. Any measurement is allowed. Yes. Again, one thing I didn't say is, okay, let's make some space. So okay, in general, if you have a dimension D unitary, requires it requires polynomially many in D queries, and it also requires polynomial in D time. What do I mean by time? So the time is like the time it takes to construct these measurements and the time it takes to post-process these measurements. Okay? So you should think of this dimension as being exponential. So if you have n fermionic modes, this is going to be 2 to the n. So you want to do something that's better than this. And so the lesson from a lot of this is for some classes, for some special classes of unitaries, we can do better. What do I mean by better? We can get like log D. Oops. Okay. We can get logarithmic in D time. And if it takes logarithmically in D time, it also takes logarithmically in D queries. Okay? So the goal is to find classes of unitaries such that this is possible. And we're going to find those in the world of fermions. So fermions, recall that fermions are built on these Majorana operators. I think Antonio gave a lecture on learning fermionic states. Uh, Same thing applies for unitaries. So for Majorana operators, you have, let's say you have a two, an n mode system. What is an n mode system? This means that you have like n buckets where the fermions can be, and the dimension is 2 to the n, okay? And you can define any system on n fermionic modes with these two n Majorana operators, gamma 1, gamma 2, gamma 2n, okay? And these Majorana operators have special properties. If you take any Majorana operator squared, it's equal to the identity matrix. Sometimes I might write this identity matrix as just a 1, okay? So there, it squares to the identity. It's self-adjoint, which means the Hermitian conjugate of the Majorana operator is just equal to itself. And you have this special, so like let's set A not equal to B. You have this fermionic canonical anti-commutation relation, which means that if you multiply gamma A times gamma B, this is equal to the negative of multiplying gamma B times gamma A. Okay? So these are called the fermionic canonical commutation relations, or CCRs. Okay? And this is how we're able to, each of these Majorana operators, you should think of as 2 to the n by 2 to the n matrices. These matrices are Hermitian, they're unitary, okay? And you can use them to really write any operator, okay? So, and then they have this anti-commutation relation. Okay, so these are the basics of fermionic systems. And so now, in the previous lecture, you saw something called Gaussian states. So we're going to look at something called fermionic Gaussian unitaries. Okay? Fermionic Gaussian unitaries. Oh yeah, I missed one thing. Sorry. Um, Another special property is that the trace of any gamma A1, gamma A2, gamma AK, if you take the trace of the product of any of these, this is going to be equal to 0. Okay? So this is going to be useful to know. So fermionic Gaussian unitaries, uh, what are these? Okay, so they're the unitaries that generate these fermionic Gaussian states that we learned about in the last lecture. And they're also called, non-interacting. Fermionic unitaries or states. These are called because they correspond to fermions that don't interact. So these fermions are just kind of all doing their own thing. There's no interaction terms that govern their physics. They are sometimes also they're equivalent to this class of qubit states called match gates. They are generated by something called fermionic linear optics. And what are fermionic linear optics? They're composed of these two elements called there's a beam splitter, and then there's a phase. Sorry, excuse my handwriting. Phase shifter. It doesn't really matter what these components are, but you should think of these things as like the gates that you use to generate these unitary operators. Okay, so fermionic Gaussian unitaries, what are they mathematically? So formally, U is a I'll abbreviate these FGU for short, fermionic Gaussian unitaries. So formally, U is a fermionic Gaussian unitary if for all Majorana operators from 1 to n, the conjugation action of the unitary on this Majorana operator is equal to the sum of other Majorana operators. Okay? B equals 1 to 2n. Okay? This is what a fermionic Gaussian unitary is. You can write U Majorana U dagger as just the sum of 2n operators. Normally, this would be 2 to the n, right? Because how many different ways are there to like so normally so for a non-fermionic Gaussian unitary operator, we need order of 2 to the n terms of this equation. So compare this 2 to the n with 2n over here, okay? The point is these fermionic Gaussian unitaries have a lot smaller like parameters describing them. And so this r sub a to the b, okay? This r sub a to the b, this is a matrix. R is a matrix that belongs to the orthogonal group on 2n matrices. Okay, this is the orthogonal group. What does this mean? It means that R transpose times R equals R times R transpose equals the identity matrix. Okay, so what does this mean? So the lesson here, the moral, is that every fermionic Gaussian unitary has a compact description. Okay, and the description is just this matrix R. Okay, does that make sense? Is everyone following me so far? There's a question in the chat. Okay, cool. So, right. So this compact description, because we have a compact description, what does this mean? This gives you a number of things. This is efficient to simulate. So if you start with a Gaussian state, you apply Gaussian unitary, you can simulate measurements. Okay, so any quantum mechanics, any quantum computing that is induced by these fermionic Gaussian unitaries can be efficiently simulated on a classical computer. So you can take your laptop, you can write a program that takes this fermionic Gaussian unitary, that takes this matrix R, and you can use it to simulate it, and you don't need a quantum computer. Okay? What does this mean? This means that this cannot be universal. This is not universal for quantum computing. You cannot make any random quantum, like arbitrary quantum unitary using a fermionic Gaussian unitary. If this is true, then quantum computers are just dumb, right? We could just use it on our laptop. Like we can just write a program on our laptop and then we can make any quantum computer. So we'd better hope for every one of us to have a job in quantum computing that these are not universal for quantum computers, okay? So they are very powerful, okay? Still, they show up in chemistry, in many body physics, and so many other places. They show up in the Hartree-Fock method, which is used to approximate the ground state energy of molecules. They show up in like the Kitaev honeycomb model. They show up in models of superconductors. They show up in a number of like physical Hamiltonians and like they show up in a number of physical processes and effects that, despite their succinct description, like look, we're going from two to the n to two to the n, 2n times 2n. Okay, we're going from exponentially small to quadratic. You should expect this to be a drastic reduction in strength, and yet, despite them being efficient to simulate, despite them having this succinct description, despite them being non-universal, they still have a number of applications. So we still care about them, okay? And this means that they are perfect targets for learnability. Efficiently learnable. What does this mean? You can make, so Pauli and queries leads to it leads to a close approximator. I can make polynomial and n many queries to this Fermionic Gaussian unitary, and there's an algorithm that spits out a Gaussian unitary that's close. Okay? So this is a result of Oshmaniak, Gangnam, Sultan Zimboras, and Mauro Morales. Oh, I got the order wrong. And it was a result that was published just a few years ago. Okay, and we're going to talk about that result. So, yeah, before I go any further, any questions about what we're trying to do here? So, efficiently learning fermionic Gaussian unitaries. If you want me to stop or go back at any point, just interrupt and tell me, okay? So efficient learning of fermionic Gaussian unitaries. I'm not going to go too much into depth about like proofs and stuff. I just want to give you a sense of technique. So the very, very basic idea here, the idea is you learn actually, sorry, let me change my notation here. I'm going to call this M. Instead of R, I'm going to call this M, okay? Okay, so M is sometimes called a correlation matrix. It tells you that I go from one Majorana operator to a linear combination of other Majorana operators. It tells you, the correlation matrix tells you how you go from one Majorana to a linear combination of the others, okay? So this is all the information. This contains all the information. So it contains all info about the fermionic Gaussian unitary, okay? So the idea is to learn an approximator for the correlation matrix. And then we're going to use this. We're going to use this to reproduce the fermionic Gaussian unitary. Okay, so this is going to be our high level approach. Okay, uh, and so how do we learn M? So this is like a good question. Like how do we actually learn this matrix M? There's a number of things you can do um, that I don't have time to get into in a 1 hour lecture. I recommend reading the paper, but overall, I just want to give you a sense of the techniques. So here's the idea. So we're gonna abstract this away. Um, so the measurements. So after the measurements, you get some M hats such that the operator distance, the spectral distance between M hat and M is less than or equal to epsilon. Okay? What does this mean? This operator distance right here is just the difference between the top eigenvalues of M hat and M. Okay? Or it's the difference between any two like it's like the largest singular value. Sorry, excuse me. This is like the largest singular value of their difference. And this is basically saying like how much more does M hat stretch one vector than M? Uh, okay. And then they show a lemma. So this is the key lemma. Suppose, okay. Hang on. Before we do that, so if you have a matrix M1 in the orthogonal group, and you have a matrix M2 in the orthogonal group, this corresponds to a unitary U1. This corresponds to unitary U2, okay? Every orthogonal matrix corresponds to a fermionic Gaussian unitary. So this is a fermionic Gaussian unitary. This is a fermionic Gaussian unitary. Every orthogonal matrix corresponds to a fermionic Gaussian unitary. And what this lemma states is that the lemma states that the diamond distance between U1 and U2 is less than or equal to 2n times the spectral distance between the corresponding matrices. Does this make sense? What I'm saying here, okay, all I'm saying is that the distance between the unitaries is proportional to the distance between the orthogonal matrices. This matrix tells you everything about this. This matrix tells you everything about this. So if the matrices are close, then the unitaries are close. Okay? The proof, it uses mathematical tools from representation theory. It's beyond the scope of this course, but I just wanted to give you a sense of like what kind of like what just the high level approach is. Okay, so so once you have this, the algorithm becomes the following. The first step is approximate M by M hat. And then the condition you get from this so basically you can make queries to this unitary to get some M hat that such that M hat is close to M. Okay? That's just basically comes from this. I'll abstract away how we actually do these measurements. We don't have time to talk about it. but that's the idea. You approximate M by M hat. The second step. Okay, now this matrix over here, M, this is in the orthogonal group. Why? Because it corresponds to some fermionic Gaussian unitary. Okay? This matrix, this is not in the orthogonal group. So we actually, to get a fermionic Gaussian unitary, we need to send it to the orthogonal group. Okay? So what we do is we take the polar decomposition of M hat to get M tilde. Okay? And the polar decomposition is it returns the closest element of O2n. Okay? What does it mean? It returns the closest element that's still an orthogonal matrix. So let's draw a picture. So you have M hat. Okay? It's epsilon far away from M, which is in the orthogonal group. And the polar decomposition sends you to something that is also in the orthogonal group. So this distance over here, it returns the closest thing, okay? So this distance has to be at most epsilon, okay? Because this is close to some, if this is sending it, the polar decomposition sending to the orthogonal group, this can't be greater than epsilon because then it would send you to M, okay? So it sends you to something M tilde. This is less than or equal to epsilon, okay? And what this means is that the distance is less than or equal to 2 epsilon. Okay? The distance, the guarantee is M tilde minus M is less than or equal to 2 times epsilon. And the final step is to use M tilde to build FGU U tilde. And what we have is that U tilde minus U is less than or equal to 2n times M tilde minus M. But we have from here that M tilde minus M is less than or equal to 2 epsilon. So this is less than or equal to 4n epsilon. Okay? And so we want this to be less than or equal to some epsilon prime. So we just set epsilon equal to this new epsilon prime over 4n. Okay? And that's the idea. So this is how this algorithm works. The idea is you learn an approximation of this M to get M hat. You take the polar decomposition. It doesn't exactly matter what the polar decomposition is, but you send it to something that's actually orthogonal. And then you use that orthogonal matrix to build this new Fermionic Gaussian unitary. And you can use this analysis to show that the distance, the diamond distance between U and U tilde is at most some small number epsilon. Okay? Any questions? That was kind of fast. Yeah, I'm wondering if you're so confused that you don't know what questions to ask. But yeah, oh, sorry, you have a question, Solomon?
So how do you get from M to like M hat?
Oh yeah, how do you get from M to M hat? So this involves some kind of measurement schemes that I don't have enough time to talk about. But one way to do it is called the fermionic Choi state. Um, the fermionic Choi state is like a state that describes basically the amplitudes of the state are proportional to the entries of the unitary operator. And by measuring this fermionic Choi state, so basically you apply the unitary U to a maximally entangled state, and there are certain measurements to give you M hat. So this is one way that you can do it. It's how I do it in the follow-up paper I have, which I'll talk about shortly. I use the fermionic choice state, but there's ways to do it without auxiliary entanglement as well. That just require a bit more effort. I'm not exactly sure how they accomplish this, but they talk about this in this paper. The paper title is called Fermion Sampling, and the authors are Michal Osmaniak, Damian, Mauro Morales, and Zoltan Zimboras. I believe it's on the website, right, Jinseo? I think it should be on the web. It should be linked on the website.
Yes, there is this link on the website.
Cool. Yeah, the reading is on the website, and they talk in depth about how to implement this measurement. Okay. So we're running short on time. So now I'm going to talk about the generalization. T-doped fermionic acid unitary. So recall from before, we have that fermionic Gaussian unitaries. These are not, oop, I didn't want to erase it. Okay, these are not universal for quantum computation. Okay. However, a nice fact, adding any non-Gaussian gate, this gives you if I take any gate that's not a beam splitter or a phase shifter, or a combination of them, and I add it, I like give myself that extra power, I can make any unitary operator. This is called universality. Okay? And an example is the swap gate, which basically swaps two buckets of fermions. Okay? It just swaps two modes. So you just swap two modes, and the fact is that FGU plus swap equals everything. You can get everything from this. Okay? By just taking a fermionic Gaussian unitary and putting in a swap gate. And so this is called doping. Okay? It's called doping. Yeah, I know the Winter Olympics are going on right now, so I shouldn't be talking about doping, but this is a different kind of doping that's not too bad. Okay? So doping, a T-doped fermionic Gaussian unitary, I use T non-Gaussian gates. And what does this look like? So FGU1, I'll just call it G1, okay? So you have this Gaussian unitary G1, and you have this non-Gaussian gate. Maybe I'll draw all the non-Gaussian gates in orange. I'll draw in a different color. E2, and then you have this other non-Gaussian gate, G3, and you have this third non-Gaussian gates, and so on. That's what this doped unitary looks like, and there's all like connections between all of these things, and so basically the idea is you interleave all of these Gaussian unitaries, and in between them you put in some non-Gaussian gates. And so this is no longer, these are no longer FGU. So the question is, can we still learn them? Can we still learn these fermionic, doped fermionic Gaussian unitaries? The answer, of course, we efficiently. Can we learn them efficiently? The answer is yes. And there's this paper by me last year where I solved this problem. I give you an algorithm that efficiently learns this, and the time is polynomial in n, and it's exponential in t. What is t? Equals the number of non-Gaussian gates. Actually, I think I already wrote that. Yeah, I already wrote that here. Okay. So the timing scales polynomial in n, and it scales exponential in t, the number of non-Gaussian gates. Okay. So now, in the limited time that I have, I'm going to try to describe to you how this algorithm works. Okay. So here is one way we can think about it. So we know that for an FGU, U, we have that U Majorana A dagger equals the sum of M sub A B Majorana B, B equals 1 to 2n, and that M is an orthogonal matrix. Okay, now here's where I'm going to ask for some audience participation. This orthogonal matrix M, what can you tell me about its columns? Like what kind of vectors are the columns? Does anyone know what the columns of an orthogonal matrix look like? What kind of vectors are they?
Orthonormal basis.
That's right. That's right. They're orthonormal columns, which means they are unit vectors. So here, folks, this is what a fermionic Gaussian unitary does, okay? Let's say you have gamma A, you have gamma B. A fermionic Gaussian unitary so a fermionic Gaussian unitary, it just rotates the Majoranas. Okay, here's what I mean. We're going to write this as eta sub A. Okay? Each of these coefficients makes this like a unit vector. So it's like a linear combination of this that's like a unit vector. So I rotate from this standard Majorana basis to something that's a linear combination of two Majorana operators, and then we rotate this other Majorana operator into something that's orthogonal. But I have a new basis that's just rotated over by this. Okay? So we can still think of these as like eta sub A, and these eta sub A, okay? These eta sub A, how can we write these? We can still write eta sub A squared is equal to the identity matrix. We still have that eta sub A dagger is equal to eta sub A. And we still even have that if you have eta A, eta B, this is equal to negative eta B, eta A. Okay? So actually, if you guys are having trouble following this, I think Jinsei, you're like recording all these lectures, right? I want to give you guys an exercise. If you're having trouble, prove this. And you should be able to do this within 10, 15 minutes. This should not take you any time at all, okay? But I want you to prove this on your own time. We don't have time here, but prove this to yourself, okay? Basically, the moral here, these are different Majorana operators. They're Majorana operators that are rotated. They live in this different world, but they have the same properties. They're basically Majorana operators. Okay? So I'll call them rotated Majorana operators. Okay? So basically, a Gaussian unitary rotates a regular Majorana into a rotated Majorana operator. Okay? So here is the conclusion. Here's the thought process that we had, that I had when I was writing this paper. So my friend Antonio, who you heard from last week, and his co-author Yaroslav, they showed the following identity. So if you have a T-doped fermionic Gaussian unitary U, you can write it as Gaussian. You can write it as the identity so this is Gaussian. This is Gaussian. And this only acts on T modes, okay? So basically, what you can write this as is if you have this fermionic Gaussian unitary from before, you can write it as this is Gaussian, this is Gaussian, and this is a unitary, but this is only small. Okay? What this is saying is that you can move all the non-Gaussianity. You can move all the non-Gaussianity into a small subspace. Okay? So that's what this compression lemma is basically telling you. And so here's what I was able to show. Okay? So a fermionic Gaussian unitary, you send to n Majorana operators. You send two n rotated Majorana operators, each to 2n rotated Majoranas. Okay? That's what this is. You're sending 2n. So this is true for a equals 1, for 2, all the way up to 2n. And so for any fermionic Gaussian unitary, you're sending 2n rotated Majorana operators to 2n different rotated Majorana operators. And lemma from my paper is that a T-doped FTU, you're not going to send 2n Majorana operators to 2n Majorana operators, but what you do send is 2n minus 2t rotated Majoranas to 2n minus 2t rotated m's. Basically, this whole top thing, like, look at this whole top part, okay? This still behaves Gaussian, and then this part is the only thing that messes these things up. That's why we have a minus 2t here, okay? So the point here is that the moral, even though we're not perfectly Gaussian, we still have lots and lots of structure. Okay? And you know how we're going to find these things? Here's how we're going to find these things, okay? So I want you guys to answer in the chat, okay? G1, this is a Gaussian unitary. What kind of matrix is associated with the Gaussian unitary? What type of matrix? Answer in the chat or out loud. So U equals G1, 1, UT, D2 dagger. Yeah. Did someone say something?
Orthogonal to n.
Orthogonal. So this is kind of orthogonal. And this is also kind of orthogonal. Okay. And this is like a bunch of ones and then some other stuff. And this looks like kind of like a diagonal matrix. Okay. Maybe not, it doesn't look exactly diagonal, but like the identity matrix, this is like the identity matrix, right? You're not doing anything here. The identity matrix is diagonal, right? And this is a small matrix. So this matrix, it might correspond to something that's maybe a little diagonal, but not exactly diagonal. Can someone tell me a matrix decomposition theorem where you take a matrix and you write it as orthogonal times diagonal times orthogonal? Does anyone know a matrix decomposition lemma like this?
Diagonalization.
Diagonalization makes this and this the same thing, but these are different. So almost.
SVD.
Very good. Very good. Yes. SVD. That is the answer. So here's the idea. This is the idea. Use the SVD. And for those of you who are not familiar with the SVD, this is the singular value decomposition. Arguably the single most useful matrix decomposition lemma in all of linear algebra. So the idea is that there is still a correlation matrix M. It's a 2n by 2n matrix still. It doesn't contain all of the information, but if I take the SVD of M, I get some V1, which is an orthogonal matrix, some sigma, and some V2 transpose. Okay, and so the theorem that I show is that V1 corresponds to G1, or G1 is this, it's this. From this left matrix, you can get this. Okay? V1 corresponds to G1, V2, which is this other matrix. So this is like orthogonal, this is orthogonal, and this is diagonal. That's what the SVD does. V2 corresponds to G2. And sigma you have 2n minus 2t values are equal to 1, and this is maximal. And you have 2t values less than 1. Okay? So this gives you the exact value of t. This tells you what your t doped parameter is. Okay? So here is now my learning algorithm. So the algorithm is first find correlation matrix M, and there's going to be an approximation. And folks, I'm going to be honest, an hour is really not enough time to, even if I was just to tell you about this paper, it's not enough time to tell you about all the technical work that goes into the paper. There's a lot of hard stuff that comes with approximation, but let's just take it for granted now, okay? So we find the correlation matrix M. This is no longer fermionic Gaussian unitary. It's a T-doped fermionic Gaussian unitary, but it still has a correlation matrix. It doesn't tell us all the information, but it will get us there, okay? So 2 is to take the SVD of M to get V1 sigma V2 transpose. V1 goes to an FGU G1. V2 goes to a G2. Okay? You use these matrices to construct G1 and G2. And here's what we're going to do with that. Okay? I'm going to copy and paste this. I'm going to put it down over here. And now here's the magic. Okay? Here comes the magic. You're going to take this G1. That's too big. I got too excited. You take G1 inverse. And you're going to take G2 here. Okay? You use the SVD, and you're going to use the SVD to find G1, and you're going to use it to find G2. And then we're going to apply G1 dagger on the left. Folks, what is G1 dagger times G1? What happens here?
Cancels to item.
Yes, exactly. We cancel. This cancels. So tell me, what happens to G2 dagger and G2?
Identity.
Identity, exactly. And so there's some annoying stuff. This like approximation stuff. That's like, man, it's like 5 pages just dealing with this approximation stuff. It's a lot of work. It's way more work than you would expect. Read the paper to see all the nitty-gritty details, but that's the idea. There's approximately cancels. And then what happens? Okay, are we ready to erase this? Once this cancels out, what is left over? What is left? We have U. We have U sub t on the inside, okay? And the last step is brute force tomography learning. Tomography and learning are basically interchangeable for UT, okay? And there's only T modes. Because there's T modes, this takes time, 2 to the T. And this is where the exponential time comes from, okay? And then once you do that, you're home free. Okay, so this is the learning algorithm. And like I said, there's a lot that I'm hiding. Like, how do we know that we actually get G1 and G2? We actually just get them approximately, and then we only get U approximately. It's actually not completely unitary. There's a lot of these little annoying things that happen. But thankfully, the paper is linked, but this is like the high level idea of how the paper works. I think now you're all more than ready to read the paper. Okay, so you should start with. So first, start with this paper by Oshmaniak. And then the next paper, I think this paper is I like this paper a lot. I had to spend a lot of time writing the diagrams and stuff, so hopefully you understand all the little ways I use to explain the proof. But Junseo, of course, is also he's become a master at this kind of stuff, so you can ask him for any questions. And if Junseo has questions, he'll ask me. So, but yeah, that's the idea. Okay, this is the high level approach of the paper. 30 pages of analysis. You know, you can just read through, and there's like nice diagrams that you can use to follow it. And this is how you learn the T-doped unitary operators. And one more thing is that there's a concurrent work that solves the same problem. They put out a paper about a week after me. It solves the same problem. It takes pretty much the same approach of using the SVD. Their analysis is a little different. The paper is by Sharon Austin, Mauro Morales, so same M actually, and then Alexei Gorshkov, who I met for the first time last month. That will be he's also at UMD. These people are also all at Maryland, where I guess I'll meet them next year. But yeah, they solve the same problem. Okay, so these are the same papers, or say same problems, different papers, slightly different techniques. Okay, but this is like a high level approach of like high level overview of the approaches into learning fermionic unitary operators. So we started with an algorithm to learn fermionic Gaussian unitaries. So this was just to learn FGUs, and this was to learn T-doped FGUs. Okay, so sorry, this was a little bit of a crash course. It's a little bit of a bird's eye view. I didn't get to zoom in on any details, but I did have time. So I hope you accept this for now. And if you have any questions, I'm more than happy to take them. Thanks for listening and being a great audience.
Great. Thank you very much for this amazing lecture. And is there any questions from student here?
Yeah.
I have a few questions. Firstly, you thank you for your very wonderful explanation of your paper. And in the second stage of algorithm, can we take the S3D of M efficiently because the size of M is uh,
M
R2.
is no M is 2n by 2n.
Yes.
N is small, so it's 2n
Um,
by 2n, not 2 to the n by 2 to the n.
uh,
Yeah.
okay.
So the whole point, right? The whole point is that these fermionic Gaussian unitaries have a 2n by 2n matrix, even though they live in a space of 2 to the n times 2 to the n. So they have this nice algebraic structure that allows us to do it efficiently. Does that make sense?
Yes. And secondly, uh, uh, should we know the degree T to um re- uh, execute this algorithm?
Very good question. Yes, you need to give t in advance. Yeah. Otherwise, you won't be able to recover in diamond distance. So both of these algorithms recover the unitary and diamond distance. You need to know t in advance in order to do that. I do give an algorithm that so also another theorem in my paper. There's an algorithm to find t, but only in what's called the Frobenius or the average case distance. Okay, so if something is like close to a unitary that is like has like a small t on average. Okay, on most states it behaves like this. You can detect that. Why can you not do this in the worst case? Okay, think about a unitary U that behaves like a fermionic Gaussian unitary, except it just chooses one state and it's like, you know what, I don't like this state. I'm going to do something completely random on the state. How do you find that? Right? You can't find that. It will take forever to find it. So for worst case, this stuff is really hard. But for average case, I give an algorithm that can actually find T. Okay? And this high level thing is called property testing. Actually, I think Filippo gave a lecture on property testing bosonic Gaussian states. This is a property testing algorithm for fermionic Gaussian unitaries and T-doped fermionic Gaussian unitaries. Kind of knock out two birds in one stone in this paper. So that's a theorem that kind of I prove on the way to my main learning theorem. Okay, this is all in the paper. Good question. Very, very good question.
Great. Another questions here? Then, yeah, I have small question. I think this question has come up a number of times in previous lectures, but is there any known relationship between classical simulability and efficient learnability? Do you know anything about
That's
this?
a really, really good question. I wish I had a better answer for you, but I am trying to investigate that a little bit more. I think everything we know that is classically simulable, we know we also have classical learning algorithms for it. So stabilizer states, Clifford circuits, like fermionic Gaussian unitaries, fermionic Gaussian states, bosonic Gaussian unitaries, bosonic Gaussian states, um, matrix product unitaries, matrix product states. But we have examples of states that we believe are not easy to simulate, but are easy to learn. And those are constant depth circuit states. Okay. So QNC like states that are produced by circuits that have 2 or 3 local gates and constant depth. These are easy to learn. There's this paper by Robert Huang, Anurag Anshu, Jared McLean, a bunch of people on this paper learning shallow quantum circuits. But we don't believe that we can simulate this efficiently. Otherwise, random circuit sampling wouldn't work.
Mm.
So we believe this is hard to simulate. I don't know if there's a deeper connection between learnability and simulability, but this is something that I'm trying to investigate kind of at a high level. So I'll let you know if I have anything insightful to say in a few years.
Great, great. So yeah, I
Any other
think
questions?
we can finish today's lecture today.
Okay, cool.